suitable separation technique. This is really important subject. However, I don't have much experience on it. So that is the issue. But let's go over. This Gyan program is mainly focused on media. So whatever the criteria, strategy, process optimization, selection, first of all, you have to know how to characterize media. So you need to choose right media for the right application. So we're going to start with the general criteria strategy, and then we're going to move to the media characterization. How we're going to characterize media in order to select right kind of media. So here, criteria strategy. Somehow filtration characteristic, suspension property, process requirement. So all combination is not one, but all three of them. Then what is the properties of slurry? So everything is the variable here, solid concentration, low or high. If it is low, then yes, what is the next step? If it's high, then skip next step, something like this. So the particle size and distribution, particle shape and density, filterability. Is that easy to separating a solid from liquid? What about viscosity and density of liquid? And desired output quality, required clarity of filtrate, clear liquid or some turbidity acceptable, required dryness of solid cake, presence of variable product in either phase, capacity and throughput, volume of slurry to process for unit time, batch or continuous separation, scalability requirement. Here, the selecting suitable separation techniques, most important thing is somehow you have to have experimental data. If you have experimental data, then you can actually eliminate a lot of the blocking stones. So it's more likely designing certain things. If you're designing certain things, then you have to have the at least experimental data to support it. But it's a general criteria. Oh, well, anyway, go one by one first, and then we'll discuss it later. Separation efficiency, capture rate of solids, loss of fine in the filtrate, become a yield of variable component, operating condition, temperature certainty, pressure tolerance, corrosiveness, abrasiveness of mixture, cleanability, sanitation. So also economic factor is quite big one. Capital and operating cost, energy consumption, maintenance, downtime, labor, and automation. Last one is currently a big issue. What about disposal? Handling waste, solid, liquid, emission control, safety of handling material under pressure and temperature. All those you have to optimize it. So process optimization, selection of suitable separation technology, solid liquid filtration and separation. So one is a solid phase, the other side is liquid phase and separation. Strategy of process optimization. So material characterization, perform particle size analysis, determine sedimentation rate. This is all experiment. You have to have some data. The more data, the better to come up with the right solution. Bench and pilot testing, lab scale test here. This is quite important test. Evaluate filter rate, cake formation, washing effect. That's why the before this course, somehow if we have some test laboratory, then it'll be super, so that we can have some hands-on experience and then go into the detailed equation and you can understand that. But this is studied. Anything, you have to have some sort of data to support it. And the selection of appropriate equipment, machine filtration technology with process. Process need, clear filtrate. What do we need? Everybody wants to clear filtrate. And find sometimes the product is particle, then fine particles, high solid loading, cake washing needed or not. Automation, continuous operation. So membrane filter, a pressure filter, belt filter. So which one is the suitable equipment for that special process? Process integration, combine a step like pre-coagulation, sedimentation, flocculation to improve filtration. Optimize the cycle time, back washing, cake discharge for efficiency. Certainly modeling helps. Modeling simulation helps. I believe this is the current trend. So the optimization, find out criteria. Currently, the CFD model is quite popular. So once you have modeling, then you can easily find out optimal conditions. Filtration area, in Germany, they are actually doing so-called modeling a lot, rather than experimentation. So modeling actually helps to understand the experimental data. Also, once the experimental data support the modeling, then from the modeling you can expect what to happen. So the modeling, this is what I really recommend to do modeling. That's why currently, as far as filtration modeling is concerned, Germany is leading over US. So I think something happened. They try to do modeling first. Model first. The Germany, not several, a couple of universities, they are really good at filtration. One, I already visited them. One specifically, they are actually handling liquid. The other, several others, they are only handling air side. Looks like the air side easier than liquid. To me, liquid should be a lot easier than air, as far as modeling goes. Yeah, I strongly believe this is a key. So the optimized parameters, say flow rate, pressure drop, filter area, and then monitoring and control. Implement the sensor. This is another one. Yesterday I mentioned about sensors. Currently the sensor cost is really low. So the portable unit, you will see a lot of sensors on it. Use data analytics and predict maintenance need to be optimized schedule. Types of mixtures. Particle size is core filtration, 10 to 100 micrometer. Is intermediate. What about less than 10 micrometer? Fine filtration. The centrifugation and membrane filtration necessary. A little bit big one, vacuum filtration, pressure or settling is good enough. Solid concentration. High solid concentration, certainly sedimentation, vacuum drum filter process, filter press, and low one, certainly centrifugation and cross-flow membrane filter. What about the solid property? Is that compressible or not? It is compressible, then you have to choose centrifuge or thickening method. You know, flocculant or coagulant, you have to use it. If it is not, then cake filtration or screening. What about density difference between solid and liquid? Large, gravity, small, filtration. Required product, what is your product? The filtration or filtrate or solid. So if you like, well, final product is solid, then the K is quite important. Scale of operation, batch or continuous. Filtration method, gravity, we already covered that one. Vacuum, pressure, centrifugation, membrane filtration. So membrane filtration, certainly fine particle detention, high clarity, but fouling is the problem. Centrifugation, high speed, effective fine particle, but energy cost is high. Slurry with a large particle, faster than gravity. Gravity is simple, low cost, but it's slow, not for fine. High pressure system, high efficiency, high cost. Here, this is a chart. selection of the suitable separation technology. So solid content, filter medium here is too low. Then solid content is really high. Then skip centrifugation. Go direct to thickening. If it's low, then it's going into centrifugation, something like this. Yes or no. Okay, here. Whatever it is, the media is important. Previously, we tried to find out the optimization. And so, if it is filtration, not the separation, then media characteristic require what type of media we're going to use it. Is that the centrifugation? Oh, no. The ultrafiltration or nanofiltration, anything. Then somehow we need to know the characteristic of media, right? That is the key point. So I'm going to go over this one. Oh, not yet. It's flow charging. I thought that's already over, but it's not. The solid concentration is high, yes, then go to step 2. The solid concentration is not high, then no, go to step 3, something like that. Is cake formation acceptable or desired? Yes, use filtration method. Which one? Gravity filtration, vacuum filtration, or pressure filtration? If it is no, then consider centrifugation, thickening, etc. This is same as the previous one, right here. We are talking about this one. Is the solid finely divided or colloidal? Yes, go to step 4. No, use simple decantation and screening. Is high clarity? Yes, use centrifugation, ultrafiltration, and membrane filtration. There is no sedimentation, vacuum. Is temperature or chemical compatibility a concern? Yes, select equipment material and choose based on cost. Choose technique based on above answers. That gravity filtration is good enough, coarse particle, simple separation. What about faster than gravity for fine particle? The vacuum filtration is required. What about the thick slurry, high resistance to flow? Then somehow you have to apply a pressure. The pressure filtration is necessary. What about fine colloidal solid, high clarity required? Then centrifugation is appropriate, right? Appropriate, and sedimentation thickening, low energy, large particle, continuous operation. Last one is membrane filtration. This is really a fine particle, microbial removal, certainly. Now, this is quite important. Filter media testing and evaluation. So, this is to me the first criteria we need to look at it. Because the media is the heart of filtration. So, So filter media testing and evaluation is a systematic process of characterizing filter material. Performance, durability is quite important for liquid filtration, and suitability. The other one is the comparability is important one. It involves structure, mechanical, and filtration process under standardized conditions. Here, the media characteristic. First, physical, structural characteristic. This is normally what we normally do. Once we receive the filter media, then normally we measure thickness. Sometimes we measure the density, not always. For liquid filtration, certainly porosity and pore size distribution is really important. So, liquid filtration media, we normally do the thickness. Porosity is quite important one. And then pore size distribution and maxipore. That's essential. We need to measure it. And sometimes we really like to look at the fiber structures or pore structures. We normally call it morphology. If it is big, then optical microscope is good enough, but it's not, then we have to use SCM. So water permeability, this is really important as far as the liquid filtration. And then mechanical property, tensile strength, elongation, this is more important in liquid filtration than air filtration. Bubble point, compression, the recovery, sometimes it is necessary. The media is compressible, then we have to understand what's going to happen in the field. So abrasion, flex, fatigue resistance. Last one, we don't normally do, but sometimes we can do that. Filtration efficiency, retention. Normally, the filtration radar ratio or something like is kind of costly. However, pressure drop and dirt capacity, we sometimes do. Flow rate. And last one, we don't do a lot, microbial filtration efficiency. Sometimes it is important to study the filtration. This is a special area. And functional environmental testing and chemical comparability. This is quite important. Whether it's the certain kind of solvent, then the media has to be resistant to specific that solvent, oil or acid, alkali. Thermal stability and humidity moisture resistance, hydrophobicity or hydrophilicity effect. Sometimes aging test, long-term is, to me, this is, I don't know whether it is necessary. However, in air, some area we have to do aging test. For instance, the industrial air cleaning equipment. Industrial air cleaning equipment, they do use a lot of bad filters. But pulsing, once a lot of dirt on the surface of filter media, we have repulsive. So some media probably about 50 pulse, it tears. Yeah. That's why this is quite important, the aging test. Several times pulse. How long we can do it. So we call it aging test. Yeah. So there are some test standards. How many times you have to do this, and then you can apply. Last one is probably futuristic. Later on, it might be big issue, but not at this moment. So here, filtration efficiency, particle counting, certainly pressure drop, differential manometer, you can use it. So most of the time that I spent when I was working on the company, the media testing is what I do. Certainly, we have a lot of technicians, but media testing is quite important. The other thing is the commercially available media is we normally ask roll, and then sometimes we ask beginning of the roll, and next day we ask about the other roll, so that we can look at the consistencies. And then beginning of the roll, end of the roll, and the width. Through the width, we normally check the efficiency, pressure drop, something like that. So that's the actually routine work. However, that's quite important work, real world. The media we see sometimes they make at night. They make during the day or the summer season or winter. The property is slightly different. So we don't want a lot of the deviation. We have some tolerance. There is some tolerance. So liquid filtration, this is really important. Yeah, pore size distribution. We normally call it capillary flow porometry, bubble point. This is commercially available. Yeah. So sometimes you have to use the standard material and calibrate it from time to time. So this one is quite important. That one, once you do, then you know what's going to happen. So if it is the coalescing media, this is really important one, contact angle measurement. And then chemical compatibility, this is quite important one. And thermal stability, service life. Here is the liquid filter test standard available right now. STM F795, bacterial tension, sterilizing the grade filter. This is a special application. Not all the liquid filtration application. ASTM F316, this is quite important standard. The pore size distribution related. And ASTM D3861, membrane filter evaluation in water treatment, particle retention. ISO 19438, this is a fuel filter in the automotive. ISO 4020, fuel filter testing, same thing. 16889, hydraulic fluid filter, multi-pass test efficiency. And ISO 11171, calibration of automatic particle counter. So, not many, but for us, the most important one is F316. This one has been for a long time. Yeah. Then somehow, probably you already knew Laplace equation, bubble point. Yep. Porous membrane, I should say the media is better. Porous media or filter as interconnected folds. When complete wetted with liquid known surface tension, this pore, that pore has to fill with the surface tension, low surface tension fluid. So nowadays the fluorochemical is kind of it's not really banned, but under the PFAS issue, so the alcohol-related solution, you can use it, I believe. Yeah? The gas pressure applied on one side, the smallest pore, resistor transfer. This one is we call it bubble point. Yeah? The bubble point is the largest pore, bubble up here. When you look at the Laplace equation, actually we got a Wabashi equation. The Laplace equation is before coming out the Wabashi equation. So D is pore diameter, gamma is surface tension, this is contact angle, and this is differential pressure. So this is constant. Somehow we don't care about cosine theta, consider it 1. So 4 gamma over P, that is the diameter. The method. The sample wetting. Yeah, usually low surface tension. So isopropanol water mix is good enough. Previously, we used the fluorochemicals. That one contact angle is so low, so it's a lot better. But nowadays, it's kind of under PFAS issue, so we don't use it. But some labs, they still use it because it's candy. And then somehow you have to pressurize the air in order to get the bubble point first. Then how we can get the size distribution. Once you have largest pore, then, well, you can look at the actual graph. Yeah. You do the wet run. Wet run is this one. It starts once you pressurize a little bit, then you can see bubble boom comes out. That's the largest pore. That's right here, a starting point. And then it's going up, and then it's dry out, and it's same as the drying curve there. So in the middle, half dry curve right here, that we call it mean flow pore. That's quite important. That's quite important. But we normally run dry run first and then wet run. But sometimes they do the same sample. Once you run wet run, then this point it dry out. Then you can do the dry run. And then you can compute out the pore size distribution. I believe everyone did some experiment, right? Because that lab has the parametry. So this is a quite important parameter you have to look at. The pore size distribution as well as the maximum pores.
What should be the property of wetting solution? Give some example of that.
Contact angle lowest possible. Yeah. So normally fluorochemical material is a good one. Yeah, that's a really good one. But
another point is that it should not soil the fiber. Whatever the solution you use, that should not have any reaction with the fiber. Also, it should not soil the fiber, because if it soils, then pore size will eventually.
So it has to be a hydrophilic material or some finishes.
For example, for cotton fiber, you cannot use water. Okay, because that will soil and structure of the pore will change.
yeah, correct. Question?
Your wet run curve is the one which is curved, na?
Okay, here. Wet,
Curved one is the wet run.
no, wet curve is from here going up all the way. That is wet curve. Dry curve is brown. This is dry curve. So, in fact, the angle like this, that is pore size distribution. That is pore size. Whether this one is going this way, going that way. If it is going this way, then pore distribution is really narrow. But important one is the half dry curve right here, this point. Mean flow pore diameter is quite important. So,
You will be getting the distribution graph. For example, if you took the distribution, because here if you see it is a pressure, okay, at a certain level of pressure, you are getting the first bubble to burst, means it will give you the largest size of the pore, because it will be easier to flow through the largest size of the pore. But from this pressure data and flow rate, because this is the pressure data versus flow rate. So from this, how we can get the pore size distribution? Are you getting my point? See, there are two things. One is that if you are pushing the water or any fluid, okay, gradually it will move into the smallest size pore. Okay, initially the largest pore will get open up, then it will gradually move to the smallest size. So you can have the relationship between the pressure and the diameter of the pores. pressure and diameter of the pore. Are you getting my point? Gradually you can have more water into it, so you can get the pressure versus flow. Sorry, pressure versus diameter of the pore. And if you see the Poisson's equation, there is a relationship between the pressure versus what? Pressure versus diameter.
Yeah.
So pressure will get nullified, so you can get the diameter distribution. But that distribution is based on the volumetric distribution. Okay, that is the volumetric distribution. Because in many cases there is no clarity about that thing. Okay, how you are getting the distribution? Because here it is pressure versus flow rate. So volume versus force you are getting. Volume versus force. Again the pressure versus. I mean, if you increase the pressure versus flow. Okay, or pressure versus diameter and pressure versus volume. Both will get cancelled out, so you will be getting the equation.
Okay, the
I mean, that's
This would
already
be
replaced.
applicable only for woven, non-woven, bubble
No, this is used for, this can be used for non-woven.
non-woven.
Woven fabric, it is simpler. Okay, pore size determination will be simpler. In the case of, if it is a net skin, open like of structure, it will be simpler.
well, I'll give you the my paper, the old one. I didn't bring it. Probably you already have the copy of it. One paper has equation is there, the to obtain the pore size distribution. Uh, who has?
I have sent already.
Yeah, get my paper. See, I didn't bring it.
Yeah, it is there.
Pore and permeability.
Yes.
So that you can share in the WhatsApp.
Yeah, it is there in the WhatsApp.
It is there.
It is there in the WhatsApp.
Okay. Here is the equation right there.
Yeah.
To get your thing. I don't know whether we can put it. Is that possible? This is the paper.
Open the WhatsApp. The ebook wala na? No, no, no. ये scan
So the actually you can get the pore size distribution really precisely. The equation is already I gave you. He tried to put it on there. So whatever it is, the mean flow pore size is quite important. So once you receive the media, I don't know whether you do have porometry at your place. That's the essential equipment you have there for liquid filtration.
That is the capillary flow porometry.
Yes,
Flow
correct.
porometry means is a calculation of difficulty perpendicular.
perpendicular.
Okay. But it is not like the marker inclusion porometer where you have to cut the
Oh, yes.
you have to put it in a container. So that is not a good method for estimation of it.
Yeah, he's right. There is another method, mercury intrusion method. So mercury density is really high. So sometimes the data is okay here. Can you move up? Right here. Right here. This is the. Oops. This is the equation to get the pore size distribution. Equation is there. So why don't you go down a little bit? Epsilon, I don't know whether I wrote it down some. Yes, that's good. That's good. So the equation 6 is a bit tough to understand, but the actual equation is number 4. That's the Poisson distribution. At that time, I was really a young engineer. Also, I was professor at Tennessee Tech, so I taught the flow through porous media. I have only 5 students. In fact, I started a lot. So that's why I currently once you have some sort of overview, then how we can apply it. So, okay, I believe that's the last PPT. I think.
So this is the last one.
Yeah, this is my last one. So this is last presentation. I can say the. Anyway, I enjoyed very much the last 5 days. I hope that you learn something at least what the basic principle of liquid filtration is. So liquid filtration is huge area. So I don't think anyone could expertise everywhere. It's not possible. Not possible. However, the principle is there. It doesn't change. That's why I give you a paper. It's long ago. It's 30 years ago. But principle doesn't change. It stays.
Principle stays the same, but the mechanism changes
Yeah.
in the change of application.
The Professor Mukade, he just told me that I'm a lot energetic than he does. I don't think so. However, I really want you to enjoy what you are doing. That's important. That's so. Really, I really like you to have passion to work. I don't know whether you noticed it or not. I'm 80-year-old, but I'm working like 20. Okay, that's it. Thank you.